will be focused on both mirror exploration and groundwater mapping. A brief outline of the talk. So today, we're going to start with the basic principle of induced polarization in electric and electromagnetic methods, just to be sure we are aligned on the understanding of the terms we're going to use in the rest of the presentation. I'm going to show the importance of IP modeling in airborne EM for mirror exploration, showing examples of what happens when you neglect the modeling of IP in inversion of data. Then I'm going to spend some time on discussing the link between induced polarization and hydraulic permeability. There's a focus of great importance when you talk about groundwater mapping through electric and electromagnetic methods. And with this, I'm going to show also how in alluvial sediments, so when we do mapping for groundwater exploration, I'm going to show how big the IP effect can be and how big is the error when you neglect the IP in the EM modeling. And then I will go to conclusion showing one example of airborne EM exploration for exploration of silver actually. And then I will show some of the complementarity that we have between electric and electromagnetic methods, try to get some ideas on how to apply them at the same time, maybe for reducing the cost of acquisition. And then I will go to the conclusions. Let's start with the principle of induced polarization. So let's talk the simple application. So we have 4-pole measurements. So we talk about, let's say, DC measurements, or in any case, galvanic measurements with electrodes. If we have an null space, homogeneous, isotropic, without topography, with point electrodes, and without any other source of current, all of us, we do know that the relation between the resistivity of the ground and the measurements of potential and current follows the classical law for the apparent resistivity, where K is our geometrical factor that links the acquisition geometry to the resistivity of the ground. So if we measure in a ground where there is only a resistivity and there is no chargeability, what we do expect is that for each turn on of the current, we have a voltage that follows immediately without any delay. So this would be in the top, the evolution as a function of time of the injected current between the electrode A and B. And in the bottom part, we have the voltage that we will measure between two electrodes M and N following the current injection. This is the kind of measurements that we have if there is no induced polarization, but actually when we have induced polarization, what we see is that the potential grows slowly, reaching at the end the asymptotic behavior if you wait enough time for the DC measurements. And then when you turn off the current, you see a slow decrease of the voltage. All these transients, they are not due to induction. All these transients, they happen in seconds. They are really slow compared to the induction that we might have in the first microsecond that the turn on and off of the current. So this is what we classically describe as the induced polarization phenomenon. There are simple equivalent circuits that we can use for try to understand what happens in the ground when we see these kind of voltages. And the simpler one is one where we think that if we have only a resistor, so we have only resistivity in the ground, then again we will expect a voltage that follows instantaneously the current variation. But then in a simple circuit like this, if you add a capacitor and another resistor, a circuit like this is able to produce a voltage variation similar to the one we observe in the field. And this similarity is that we have a rise of the potential where the difference of potential during the rise depends on what the resistance of the ground, the resistance of the equivalent circuit, both R0 and R1, but also this relaxation time depends on these capacitance. So this means that this kind of phenomena might be due to the accumulation of charge in the ground. So this is why we talk about induced polarization or capacitive effects in the ground. The classic way of discussing these IP phenomenon is to extend the classic Archie's law that describes conduction. We do know that the classic Archie law tells us that the conduction happens in the ions in the solution in our medium. So if we turn on an electrical field, and we will have our ions that flows in the fluid, and this current is going to be the current that give Ohm's law practically. And here what we can say is that the information resistivity depends on the water resistivity through the formation factor, and the formation factor depends on the porosity and compaction of the medium. So this is the classic law, Archie's law. But actually, we do not have only conduction in the water through the ions, but we have also conduction at the interface between fluid and rock matrix. And if we are not in presence of ores, so if there are no conduction in the medium itself, but only the surface, this conduction happens in the double layer interface between, for instance, grains of sand and water. So this means that together with the conduction to the ions, we have also the conduction to the surface of our grains. And we can imagine this conduction somehow is a conduction that goes through to the surface. So in this kind of image, we do not consider conduction through the medium itself. So far, we do not have polarization yet. For any polarization, what we need is something where when we turn on the electrical field, we have a polarization of the medium. With this polarization, practically we have an accumulation of charges that polarize the medium. So overall, we can think several mechanisms for this polarization. We have the electric double layer that we were discussing so far that gives rise to grain polarization, but this mechanism is present also when we polarize not only the grains but also the pores of the medium itself. We have the membrane polarization that acts actually not on the ions that flow through the surface of the grains, but the ions that are in the pores that are not able to pass through the narrow pores of our rock matrix. And then we have the electropolarization. That is the one that actually is we are interested in when we look for a mirror exploration, because actually in this case the polarization is there because of the polarization of the metallic grains of the ores in the rock matrix. In any case, with all these possible sources of polarization, we can think that our total conductivity in the ground is the bulk conductivity through the ions in the solution, the surface conduction plus the surface polarization. And then this means that usually when we do galvanic measurements, we measure the combination of these two when we do only DC measurements, while we can access the surface polarization measuring IP. And with IP, it is then possible to distinguish between bulk conduction and surface conduction. And this can be really helpful, for instance, for lithological discrimination, or as we will see also for estimation of hydraulic conductivity. One formula that is used really often for describing the induced polarization phenomenon, it's a phenomenological formula that many people that work on theory of IP, they do not really like it a lot, but actually is the formula is used more when we go to field application of IP. And in the Kolokov formula, we have our complex conductivity that depends on actually 4 parameters. We have the DC conductivity sigma 0, the chargeability M0, the relaxation time tau, and the frequency exponent C. And as we see in this formula, this conductivity is a complex conductivity, so it depends on the frequency that we do apply. So this is the frequency domain formula for the complex conductivity of the Kolokov model. And again, we have 4 parameters: sigma 0, M0, tau sigma, and C. So if we want to describe polarization, instead of having only 1 parameter per investor cell, that can be resistivity, we often need to go up to 4 parameters. So 4 parameters that describe actually a simplistic model of the IP phenomenon. So if we look at this complex conductivity and we look for the real part and the imaginary part of the complex conductivity, then we see that sigma 0 is the limit for a frequency that goes to 0 of the imaginary part of the real part. and sigma 0 over 1 minus m0. This is the infinite frequency conductivity. The peak of the imaginary conductivity is at the inverse of the relaxation time, while the the parameter C controls the shape, the width of this peak of the imaginary conductivity. So this is the way in which these 4 parameters affect the spectra of the induced polarization. For understanding how this formula plays a role in electromagnetic methods, it's actually easier to rewrite it. And we need to rewrite this formula in terms not of the DC conductivity, sigma 0, but in terms of the infinite frequency conductivity, sigma infinite. So if we now try to rewrite the formula in terms of sigma infinite, we get this. So from this formula in terms of sigma 0, we go to this other formula where simply we expand this summation. We can rewrite the formula like this. But if we write a formula like this, then we can recognize that if we think our current density as the multiplication of the conductivity for the electrical field, then we can say that our total current is equal to the current due to the infinite frequency conductivity minus this current here. And this current is actually our polarization current. So in other simple words, when we have IP, we have a polarization current that is proportional to the eddy current when we have EM, but this proportionality goes in the opposite direction. So we have a current that goes in the direction that is the opposite of the current of the eddy current that builds up because of polarization. So let's see what this means in terms of EM signal. So let's consider a simple medium. So we have a 4-layer medium with 2 conductive layers, 30 meter and 10 meter, and 2 less conductive boluses in medium at 100 meter. So this is the typical, so this is how the eddy currents build up in the ground. So as a function of time here, we have in blue and red the eddy current that flows in the ground because of the turnoff of a current in a transmitter for time domain electromagnetic measurements. So this is what happens when we have only conduction. But if we have polarization together with the current that are our eddy current, we have also somehow the polarization currents that go in the opposite direction. And actually, this image here is not correct in terms of timing, because what we have to think is that if these are our eddy current after, I don't know, 21 microseconds, our polarization current will be in a different place, because this polarization current, they do decay like a polarization phenomenon in a slower way. So this means that while our eddy currents, they already reached, for instance, the second layer, our polarization currents, they will still be in the first layer. And the sign of this current will be opposite. So what does that mean? This means that together with the signal that we will receive due to the eddy currents, we will get a signal of the polarization that somehow cancel out the signal of the eddy current. And this effect is stronger for late times. And if the IP effect is strong enough, then we might have at late times also a change of time. So somehow, again, this polarization phenomena for EM measurements means that whenever we have eddy currents that start to flow in our ground, there will be polarization current that flows in the opposite direction. And this polarization current, they decay slower. So this means that while our eddy currents, they go deeper in the ground, the polarization current, they're still in a layer that is probably above. Once we have this idea of how this IP phenomenon works and how it affects the EM data, let's see what happens when we have a forward modeling of EM data on a polarizable ground. So let's say that this is a decay normalized by the transmitter area of dPdt as a function of time. And here, all the gates circled are negative gates. So this is a typical EM data that we might acquire in mirror exploration, where we have for late times a change of sign for DPDT. And this change of sign, again, is due to the polarization current that goes in the opposite direction compared to the eddy currents. The typical thing that has been done for decades has been simply to take all the decay, remove the negative data, and try to invert and interpret this negative data alone. If we keep all the positive data before the general sign, often what we see is that we are not able to fit the data well enough. But then the typical strategy in the industry has been to, so this is something where maybe also from the inversion model we might recognize that something goes wrong, because in this case, for instance,
Gianluca, apologies to interrupt you. Since you're the host, there's a few people waiting in the waiting room. Would you mind just admitting them, please?
Ah, yes, sure. I didn't figure out that they were waiting for me. Sure.
Thank you so much. Apologies for interruption.
No, it's fair. Actually, you had to interrupt me before that.
Thank you so much.
Okay, I think I muted all, right?
Yeah.
Okay,
thank you.
So we were saying that a typical effect of this IP phenomenon, when we simply remove the negative data, is that the resistivity, in this case of the last layer, becomes too high. And it becomes too high because the DPDT drops too fast versus 0. So the typical solution for this was simply to remove more gates. So instead of keeping all the positive gates before the general sign, we can remove some of them and try to invert again. So in this case, we fit the data really well, and we get the inversion model. The question is this model of any use? For checking if this model is of any use, we can, these are synthetic examples, so we can go back to the true model that has been used for creating this sound. So with this data, we invert this data, but the inversion model is pretty similar to the true model in any case. So the black line in this case is the fit of the data, where we fit also all the negative data. In this case, what we need is to invert for 4 parameters, and these parameters are actually, in this case, the resistivity. This is the DC resistivity. Then there is the phase of the IP phenomenon. This is, we can think this as the ratio between the imaginary conductivity and the real conductivity. Often, the phase of the IP phenomenon is the parameter that is more affected by the IP phenomenon. So in this case, but here we're in model space. So resistivity, phase, optical Cole model, relaxation time, and C. But if we simply look at the resistivity model itself, now we're going to compare this model with the model we got from the resistivity only inversion. So in this image, we have to get the resistivity only inversion with the continuous line and the true resistivity model with the dashed line. So here the question is that actually the resistivity only model has no good use at all, because not only we have wrong resistivity, but we have also wrong thicknesses. So the approach of removing negative data to the data affected by IP and inverting them with a classic resistivity inversion code, actually it does not work. It gives wrong resistivity and wrong thickness of the layers. So far we've been seeing models where if we see the phase has really big values. Here we are at phases of 300 milliradians. So these are phases we might find in exploration for ores, because these values of the phase are really, really high. So these are not the values that we typically see when we go, for instance, for groundwater exploration in alluvial sediments. So let's see what happens when we have alluvial sediments in terms also of value of IP parameters. But for going there, we do an intermediate step. So what we do is that we talk about the link between induced polarization and hydraulic permeability and hydraulic properties in general. Because once we establish this link and we see how well this link works for galvanic ground data, then we can use this link also for doing realistic estimation of IP properties on aquifers, and then we can simply establishing hydrological properties of the ground. We can see how big will be IP effect both on galvanic data, but more importantly also on electromagnetic data. So what I'm going to show now is the link between induced polarization and permeability / hydraulic conductivity found in the lab. So in the induced polarization community, actually, there are at least two approaches that differ significantly one from the other. And what I'm going to try to do today is to put these approaches together just to see how well they work together. So the first approach links the permeability to two properties, the formation factor and this S-pore. S-pore is the surface area per unit volume. So S-pore tells us in a unit volume how much surface we do have. So we can think that, for instance, in clays where the grains are really, really small, we have way more surface than in sands where the grains are bigger and then the surface per unit area is smaller. So here, this is a phenomenological relation between permeability, for going from permeability to hydraulic conductivity, we need simply to multiply by 10 to the 7 at 25 degrees. So here we have permeability, and then we have formation factor, S-pore, and then three constant A, B, C that were found by fitting of lab results. The second approach is an approach that links actually the dynamic pore radius lambda and the permeability and the formation factor. So these two approaches are the two approaches have been used more in the literature and in the lab for experiment. How do we link these two approaches to IP? Because no one of these two formula is directly linked to IP. But for the first approach, the link is actually that the imaginary conductivity is a good measure of the surface area per unit volume. And this CP is a constant that is a good constant for many sand, clay, and sand samples all around the world. So the idea is that sigma second is somehow a proxy for a S-pore. So for finding a S-pore, we can simply use sigma second. So this means that some authors in the lab, they succeeded to link K directly to sigma 0. That means the formation factor, and sigma second that stays here instead of the S-pore. So now we have an equation that links hydraulic properties and electrical properties. And these constants are empirical constants found through fit of lab data. All these kind of equations, they work only on consolidated samples saturated with water conductivity of 100 millisieverts per meter and with a specific electrolyte. But the good thing is that this formula really depends weakly on the water conductivity. So this can be used in a much wider set of situations. And this is the kind of link that was found in the lab between K measured through hydraulic methods and K estimated by IP. The second approach from under review, for instance, and other authors, links the relaxation time of the IP phenomenon to the lambda and the diffusion coefficient D+ of distant layer. So here, with this approach, what we do is that we can find the permeability through the relaxation time of the IP phenomenon. This D+ is the diffusion coefficient of the ions in the distant layer. That actually is different for sand and clay, according to under reveal. And then here we have again the formation factor. So these two are two different approaches, but again, they are approaches that link IP properties to permeability. So we link here electrical properties to hydrogeological properties that can be used directly, for instance, for modeling flow, for modeling transport in our aquifers. So the idea in the results I'm going to show you in the next slides is to put these two approaches together. So say that the permeability derived by the imaginary conductivity and the permeability derived by the relaxation time, they should be the same. So in this way, what we can do is that we can express our total imaginary conductivity as a function of for instance, water conductivity in the ground the imaginary conductivity sigma second, and this relaxation time T plus, and this diffusion coefficient T plus in the stand layer. So, and the formation factor, for instance, is something that we can keep constant in our inversion. Using this kind of petrophysical relation, it's actually possible to invert directly for hydraulic properties IP data. So what I'm going to show you now in the next slides is the estimation of hydraulic conductivity from induced polarization galvanic data in the field. So we have galvanic electric measurements, and we have measurements in 3 boreholes in Greensted in Denmark, and then 2D IP profiles from 5 different countries in Europe. So the first example I'm going to show you is an example in Greensted. It is a small town in Denmark, where we had 3 boreholes where we did electrical logs, E1, E2, E3 in these maps. And these boreholes, they ranged between 10 to 30 meters in depth. And we were measuring IP in the boreholes every 20 centimeters with a logging tool. And then the verification for this kind of data were 54 samples of grain size analysis and 9 slag tests on these 3 boreholes. In this figure here now, for E1, E2, and E3, so for the 3 boreholes, we have in the black line, this is the estimation of hydraulic conductivity from IP data. The red points, they are the grain size analysis estimation, and the blue points are the slag test estimation. So this is E1, E2, E3, so the 3 boreholes. As we see, as a function of depth, the trend of the estimation of the hydraulic conductivity follows really well the data from grain size analysis and slag tests in all the 3 boreholes, where actually the water conductivity was really different, but also the composition in terms of ions of the water. We have only a few outliers, let's say, but they do correspond to really, really thin layers that we were not able to resolve with this geophysical method. What I'm going to show you now is a cross plot of the K measured and K estimated from IP for all the 3 boreholes. So as we see, we find the right values in the right range. So we are within 1 decade on average from the estimates with grain size analysis and slag test. And actually, this is a quite remarkable results considering that in the lab, the quality of this match is still within 1 decade. At that 1 decade for flow modeling or transport modeling is good enough for doing a significantly improved estimation once we know what the values are. This is for the same type of data, the link between D plus, the diffusion coefficient in the stand layer, and the K evaluated by IP. And again, this D plus value that we do estimate, they go in the range that was predicted by Reveal. So also this kind of parameter looks like it makes sense. Just to finish this part of the presentation, these are I'm going to show you the results from the 2D profiles, and they are from 5 different countries: Denmark, Sweden, Germany, the Netherlands, and Switzerland. We have as a comparison for establishing the quality of the feed, grain size analysis and slag test again. The first example is from the Netherlands. It's actually a short profile acquired really close to the sea. So this is a situation in which we have a strong gradient in the water conductivity. In this case, we have a fresh water lens on top of seawater with really, really high conductivity. So this is the total conductivity compared to the water conductivity itself. But what is most interesting in this side is the estimation of the permeability. So here, our imaging of the hydraulic conductivity actually tell us that there is a clay layer with low permeability in the left part of our model. If we compare these results with the geologic model with estimation of hydraulic properties that you can retrieve from the geological surveys of the Netherlands, we can see that the match between the value of the hydraulic conductivity estimated from IP and the value that we have in database is quite good. So we are able to image this clay layer, despite we are really in a situation where there is a super strong gradient in water conductivity. For the other 4 tests, because it's going to take too long to explain all of them in details, I'm going to show you only the cross plot. And again, here we have KIP versus K measured in Denmark, Germany, Switzerland, and Sweden, and all of them, they fit really well within 1 decade, one from the other. So all of this to say that we can link through this petrophysical relation electrical properties and hydraulic properties in the ground. How can we make use of this link also for doing a test on EM data? Before going there, for these kind of results, we have 2 papers published. Where we have the results from Denmark, from the borrow measurements, but also from surface measurements, and we have 2 new presentations that we're going to give in September in France with this estimation that takes both approaches for the permeability estimation. In any case, going back, let's see how we can use this kind of relation that are valid for electrical methods for electromagnetic methods. So here the idea is to do for a model of airborne EM data using a synthetic 3-layer model. We describe this 3-layer model in terms of hydraulic properties, and then using this petrophysical relation, we transform these hydraulic properties in electrical properties, and then we see what is going to be the forward data with these properties. Then I'm going to do another example. In this case, we do a ground-based towed system, always an electromagnetic system, where we do for a model of data using the IP model retrieved by galvanic data. And then I'm going to show you a teaser for a research we're still conducting, where what we're trying to do is to invert directly electromagnetic data in terms of hydraulic conductivity, using the petrophysical relation that works well for galvanic data. So let's start with the first of this example. So here we have two type of lithologies that we're going to mimic, clay and sand, and we have 2 values for the hydraulic conductivity. That's a different 6 order of magnitude one from the other. For the same clay and sand lithologies, we use for this diffusion coefficient in the sand layer the value proposed by Reville in the literature. We use 50 millisieverts per meter for water conductivity and for measure factor of 5. So with these properties, there are hydraulic properties and electrical properties, we can, in a unique way, define the equivalent Kolkol model. So we can define completely the electrical properties of the ground. So the idea then is to do a 3-layer model, so sand, clay, and sand, where the first layer is 50 meters thick and the second layer 50 meters thick as well. And we mimic the data we might measure with a Skyton system with 30 meters of elevation from the ground. So let's start to look at the forward responses. We are going to show 3 kinds of forward responses. One with IP. So we take all the petrophysical relation we have seen so far, we compute the complex conductivity, and then we do the forward response of EM data, time domain EM data, taking fully into account this complex conductivity. And we will get the reference forward response. But then what we're going to do is to do 2 other types of forward responses. One, using only sigma 0, so the DC conductivity of the Kolkol model. So disregarding completely all the IP part of the formula, and the other one is quite similar. So instead of using the DC conductivity, we use the infinite frequency conductivity. So the idea is, are the forward data with IP and without IP the same, or do they differ significantly? Let's start with the comparison with and without IP, comparing with the only DC conductivity. So here we have the data in dBdt for the Skyton system. Sorry, here there is a typo. So this is dBdt. So here we have the data as a function of time, and here on the right panel we have the data misfit. So the total data misfit, if we do the forward response without IP, is around 2. A misfit of 2 is way too high than what we can expect and accept in an airborne EM inversion. So this means that simply a mixture of clay and sand in the ground, they give rise to an IP effect that is significant, they is so big that we have twice the misfit what we would like if we disregard the IP phenomenon. And this is not because we used the DC conductivity, because if we go for sigma infinite, so for the conductivity at high frequency, the misfit is even higher. So we are at 2.4. So all of this to say that if we have a decay like that, and this decay comes from a chargeable medium, there is no change of sign. So it's really difficult to claim, looking at the decay, that this decay is affected by IP. But the problem is that normal IP values that we might find in clay and sand, in aquifers with clay and sand, these IP values, they would be enough to affect the data significantly. And disregarding this IP effect, when we invert the data, as we usually do only in terms of electrical resistivity, will mean that we will get a bias in our inversion. Hopefully, it's only a bias in the resistivity value, but we might also have problems in terms of thicknesses. And the fact that, so here the message is that the IP phenomenon always affects the EM data as well. Actually, my claim is that the IP phenomenon affects the EM data even more than the DC data. And we should try to find a way of taking this into account in our inversion for the future. Another example that shows how strong this IP effect is on EM data is an exercise that I did mimicking, in this case, not the Skyden system, so an airborne system, but this TTEM system. There's a towed system where we have a transmitter 4x2, is towed on the ground, and then we have a receiver 7 meters after the transmitter. So with this system, it's possible to acquire 1,500 hectares of data per day, with sounding spacing of 5 meters along the lines and distances between lines of 10 to 20 meters. So it's possible to acquire really a lot of data. So what I did was to take one IP model derived from the galvanic IP data acquired on the site. And then with this model, I did the forward response of the TTEM data, again, with and without IP. And here the misfit, if we disregard the IP phenomenon in this site with a thin clay layer in the first 10 meters, is a misfit that goes up to 5 for the early gates. So this means again that neglecting completely the IP phenomenon in inversion of the EM data can give problems, because we might end up with a bias in our resistivity model. The last example on this IP effect on EM data is more on the positive side. So can we try to use the petrophysical relation that we've been using so far for the galvanic electric data for trying to estimate the IP phenomenon also on EM data. So here I'm going to show you a brief example. There's a teaser of a research project we're still carrying on, where I show you some data of a survey carried out in Brescia, close to Milano, in Italy. This is for aquifer characterization. This survey is 2,009 kilometers, around 3,300 square kilometers, so it's a small survey. And here we have the classic inversion in terms of resistivity. So this is not the entire survey, so this is a subset of the survey with a few hundreds of sounding. And in this kind of inversion model, we have this is around 400 meters in depth. So, and it's a few kilometers in length. So here we have this resistive layer that are above 100 meters. That should be somehow our aquifers, while our conductors around 10, 20 meters, these are the clay below our aquifers. So this is the interpretation in terms of resistivity. But the question is, can we try to invert, as I've been showing you so far, also in terms of hydraulic conductivity EM data? For doing that, the problem is that in comparison to galvanic data, when we look at inductive data, we have way less information for retrieving the IP phenomenon. So the equivalences are very, very strong here. But the idea is that we try to fix the formation factor to a value, for instance, 5. The good thing is that the petrophysical equation that derives hydraulic conductivity from the formation factor has a weak dependence on the formation factor. So even if we're off of a factor of 2, this is not going to affect too much our estimation of the hydraulic conductivity. And then what we did was to fix the water conductivity in this model based on prior information. this is a study for aquifer characterization, and actually this study has been carried out paid by the management of the groundwater in the area. So this means that we have a lot of information in terms of borers, for instance, on the water conductivity, on the water electrical conductivity. So what we did was to fix the water electrical conductivity to two values, 55 on meter and 40 on meter, below and above 100 meter depth, because we do know that the shallow aquifer has a water conductivity around 40 millisiemens per meter, while the deep aquifer has water conductivity around 55 millisiemens per meter. So fixing the water conductivity in this way, fix also the formation factor, it's actually possible to invert this data, this EM data, in this case directly in terms of hydraulic conductivity. Here again, the unit is meter per second. So here, what is the advantage of trying to do something like that? First of all, in this kind of inversion, we're also modeling IP. So this model takes into account also the IP phenomenon. So hopefully the bias is smaller in this model compared to the inversion resistivity only. But then again, being able to image directly hydraulic conductivity in the inversion might mean that we might try to use this data directly, for instance, for trying to do some groundwater flow modeling. And if this modeling works well, then we might really be able to start to image hydraulic conductivity. So this is still actually a research that is ongoing. It's not at the stage of a dream, but it's still at the stage of a work in progress. But the good thing is that in this area, we're able to obtain the same misfit of resistivity on inversion. So we fit the data really well. And actually in this inversion, we use something like 7 petrophysical relations. So it's not so obvious that using so many petrophysical relations, we're still able to fit the data well. We get reasonable K values comparable to the one we have in close borers in terms of flag test or pumping tests. The major problem we have so far, and we're working on it, is to try to fit the data also in areas where the medium is not saturated. So in areas that are really resistive because the water table is 20, 30 meters below ground, we're not able yet to fit the data as good as resistivity only inversion. And this is because in our petrophysical equation, it's quite difficult to take into account also the water saturation. In any case, all the take-home message so far is that the IP phenomenon strongly affects also EM data when we do groundwater exploration. And the standard is always to neglect this IP phenomenon on EM data used for retrieving aquifer characteristics. But actually, this might give problems because the IP phenomenon affects significantly also the EM data. Now we change completely the topic and we go to the other world of IP in EM. There is IP in EM for mean exploration. So now I'm going to show you an example. It's an example of application of 1100 kilometer of acquisition lines with approximately 30,000 soundings. It's exploration actually for silver somewhere in the world. I'm going to leave the presentation of this work next September in Brisbane. So I will give more details about the location of the site in Brisbane in a few months. But I think it's enough now to show you some of the results, even if I'm not disclosing yet where this site is. So I'm going to show you depth slice from 2,000 meter in elevation to 1,400 meters. So it's 550 meters of depth slices. I'm going to show two inversion parameters. So the resistivity, the DC resistivity, and the phase. So again, this is the ratio between the imaginary conductivity and the real conductivity. And I'm going to show you three different inversions. One, there is only resistivity, removing the negative data, so the things we should not do. Then there are two different inversions in terms of IP with two different starting models. Phase equal 20 milliradians and phase equal 50 milliradians. 50 milliradians already is the high end of phase that we might expect when we look at alluvial sediments for groundwater exploration. So 50 milliradians will be a really, really fat clay. So these values are so high because here the polarization phenomenon is because of the electropolarization, and the values that we get for the phase are much higher than the one we can expect from clay and sand. Actually, again, inverting for IP-EM data has significantly stronger equivalences than IP data from galvanic data. So this means that I'm going to show the inversion results with the two starting models with slightly different Corot scale, and this is because the final value of the parameter, it depends on the starting model. However, the model with 50 meridians is really shows a lot of characteristics that we hope are going to help the exploration of the site. And we have, in this case, also many kilometers of galvanic ground IP measurements on the site, where we can do a comparison of the anomalies that were found with the galvanic IP compared to the anomalies that we found with the inductive IP. Together with these step slides, I'm going to show also ratio of misfit. Misfit, if we invert only with resistivity, divided by misfit when we take also IP into account. And I'm going to show some example of data in feet, and also a comparison of the airborne EM results and the galvanic ground-based results. So let's show the model now. So we have three columns here. So on the left, we have the resistivity only inversion. In the middle, we have the IP inversion with a starting phase of 20 milliradians. And on the right part, we have the IP inversion with 50 milliradians as starting value. So you should focus your attention on the phase of this inversion with 50 milliradians and also on the resistivity, because these two images, they're going to tell us something about the site and possibly about the mineralization we're looking for. So from 2000, we go to 1900 meter in elevation, and here we start to see a lot of structure. So we see these conductive anomalies that goes in this direction. This is the known expected direction of the mineralization, and these are lines that are many kilometers long. So we start to see a lot of this structure in the resistive area, and we start to see also a lot of surface chargeability that will give a lot of also negative data in the data. But the interesting part is when we go deeper. So here we're at 1800 meter, and here at 1700. So here all these IP anomalies, they are quite deep. They are elongated in the right direction in terms of prior information, and they match quite nicely with the IP imaging that's been done in the ground. So these are the veins. These are the elongation of the IP anomaly that were found in the ground, and there is really a nice correspondence between the place where we have IP anomalies in the ground and the place where we have IP anomaly in the airborne data, in the inversion of the airborne data. And again, the direction of these anomalies is really matched well, comparing the ground-based data and airborne EM data. But again, the ground-based acquisition has been done in this area, but this ground-based acquisition has been way more time-consuming, expensive compared to the airborne EM acquisition. Going on and on, again, this comparison is still good in this step range between 1700s and 1600s meter in elevation. This map here is actually the ratio is for each sounding position is the ratio of the misfit of the resistivity only inversion divided by the misfit of the IP inversion. So here we see only the soundings with improvement of misfit above 30%, but this improvement of the misfit is from 30% when we have the dark blue up to a factor of 50 when we go to the red area. So overall the fit was better than the misfit. The total misfit was less than half of the total misfit of the resistivity only inversion. Sorry, I don't see well my screen. Sorry a second. Sorry, I had to interrupt because my screen was not working properly. So I'm going to show you a few data along this line. So along this direction, these are the type of data we did acquire. So in this case, we have the sounding position in the X, the sounding number actually, and here we have the decay in the PDT, one gate after the other. And all these red points here are all the negative data. So this position, this is a typical sounding that we were inverting for. So this is the type of data that we acquired and the type of data that we can fit with this kind of model. Finally, for this site, the comparison between, this is actually the second last thing I'm going to show. So this is the phase, so the IP that has been imaged from airborne inversion. And here in the bottom part, we have the phase that was imaged from the galvanic data. And again, there is a really nice correspondence between the anomaly found on the ground and the anomaly found from the airborne data. This actually here, we see the anomaly more on the right. But again, in this place, for instance, here there is also the boron formation superposed to the IP anomaly in the ground, and the place where they found the mineralization is the place where we have the maximum hour phase in the airborne IP inversion. To finish with this example, here we have two depth slices at 1,750 meters in elevation in resistivity phase on the left, and here we have the other two parameters, so tau and C. In this inversion, actually, tau and C were not allowed to change vertically. So tau and C, they were allowed to change only horizontally, and this was due for trying to diminish the equivalences in the IP inversion of the airborne EM data. And the interesting part is that also here we see that there is a nice correspondence between the chargeable anomalies and these tau anomalies, and the values that we found around 10 to minus 2 seconds, values are compatible with the literature for IP anomalies for this kind of deposits. We finish with the last topic of this presentation really briefly, and it's about the complementarity between electrical and electrical methods. So I'm going to show you synthetic example really briefly, and the idea is to take together a VES sounding, a vertical electrical sounding, with electrospacing with the AB alpha that goes from let's say meter to 600 meters. A sequence of 25 parapods. So this is our full sequence where we have all the data of the sequence. But then we split the sequence in two parts. One top part where we have only 10 parapods on the top data, and then only 12 parapods on the bottom data. So here the idea is that can we put together airborne EM data and ground-based data, maybe removing the top part of the ground data or the bottom part of the ground data, still getting a good model. Because, for instance, not having to do all the shallow part of the IP acquisition in the ground will save a lot of money. Or on the other hand, if we do not need all the deep parapods, again, this will save a lot of money. So here the question is, can we put together a vertical electrical sounding and an airborne sounding to gain information from a joint inversion? So in this case, for this vertical electrical sounding, we are modeling time domain MP data. We have a 2% noise on DC and 10% error bars on induced polarization, and we have a quite wide acquisition range from 3 milliseconds to 12 seconds. So this range is wide, but it's not fully unreasonable. The only thing is that in this modeling I'm showing you now, we do not take into account the EM induction. But for applying this joint inversion of real data in the field, then we will need to model EM induction, because we have EM induction, if you go with a AB alpha to 600 meters, is going to play a role also on the data. For time domain EM data, I'm going to show a typical Witten system with 36 gates from around 13 microseconds to 10 milliseconds. Typical Witten noise values, and I'm going to show 2 layers and 3 layer models, but with 2 different values of tau, 1 millisecond, so high frequencies, or 100 milliseconds, so low frequencies, to see if in both cases we can get something out of putting together these 2 data. So here we have the vertical electrical sounding with 25 parapods. So here in this plot, we have here AB half as a function of depth. This is the way in which we describe our vertical electrical sounding. And then in the other 4 columns, we have the model. So this is a model with a two-layer model with resistivity close to 20 meter and 500 meter, I think. The first layer is conductive and chargeable. And we have also, for relaxation time and C, we have no vertical variability. So here, the dashed line represents the uncertainty on the model when we invert galvanic IP data alone. In the bottom panel here, I did put together EM data and galvanic data. So the data is not only the vertical electrical sounding, but also the DBDT curve. In this case, we have a change of sign here. So this is a situation in which the IP is strong enough for giving negative data at the late times. If we put together these 2 data sets, the model improves. But the problem is that the vertical electrical sounding by itself has a good resolution. What happens now if we remove part of the data? So what I did here was to do again the same modeling on the same model, but removing all the shallow parapoles. So taking a vertical electrical sounding where there is only the deep information. In this case, if we look at the resolution of with galvanic data only, the resolution is much worse. We're not able to find the correct thickness of the layer. But if we put together now galvanic data and EM data, then we retrieve again a model that matches really well and has a small uncertainty on the thickness of the layer. This is true for tau 1 millisecond, but so this where the deep data, but it's the same with the shallow data. If we acquire only shallow data, we don't have enough resolution, but if we put together EM and vertical electrical sounding, then the resolution improves a lot. This is true for tau 1 second, and it's true also for higher value of tau. So full decay, only deep data, low quality, we put together EM, we find a small uncertainty on the model. Shallow data is the same. So also for a 3-layer model, we get the same type of results. We'll go quickly. So conclusion. So the IP effect influences strongly both the electric and electromagnetic measurements. It should not be neglected in mere exploration. If you neglect negative data in your transient, then you get the wrong model. But it is also important for groundwater exploration. The problem is that it is much more difficult to resolve because usually in groundwater exploration, the IP is not strong enough for giving negative transient in EM measurements. The direct inversion for hydraulic conductivity works really well for galvanic data, and we have an estimate that often falls within 1 order of magnitude from the hydrogeological estimates. This has been proven on many profiles from many countries in Europe so far, but maybe it's still a work in progress. It might be possible also to try to extract information on hydraulic conductivity also from airborne EM data. If we succeed, this would be like finding the holy grail, because being able to image hydraulic conductivity with galvanic method will really mean be able to do it at a big scale. When we have strong IP effects, EM data alone are enough for retrieving reliable IP information, and these IP anomalies, they match well with anomalies that you can find in the ground. But again, with airborne EM methods, this becomes much cheaper to achieve. Finally, E and EM data, they are complementary on random frequencies that go from high frequencies to low frequencies. So this means that we might think for the future a combination of acquisition of galvanic and inductive data that can allow us, for instance, to cut down acquisition costs, hopefully significantly. With this one, I have finished it. So thank you very much for your attention.
Thank you so much, Gianluca. While we wait for the questions from the audience, just wanted to ask you, very interesting presentation, and huge thanks for sharing your thoughts on this. Just a comment from your side on the effects of lowering base frequency of the EM system on the IP effects.
So of course, if you lower your base frequency for the EM acquisition, you start to acquire later and later gates.
Yeah.
And longer you acquire, stronger you will see the IP effect, because we always to think that if these polarization currents they go to zero slower, then they will always give an effect on later times compared to the layers where they do happen. So longer we acquire, more probable it is to start to have some IP effect that kicks in our decay. So my expectation is that longer we acquire, stronger IP effect we might see. The problem is that longer we acquire, maybe more the motion in the system is going to affect our data as well. So it's going to be a challenge, and we always to be sure that we're not trying to fit with IP motion of the system, for instance, but lowering the frequency can be a way of getting more IP data.
Okay, perfect. Thank you so much. Just a general question from Ray Durheim. Italy is prone to earthquakes, which may cause liquefaction. To your knowledge, can E or EM methods be used to assess liquefaction hazards?
This one, actually, I do not know. But in terms of hazard, what we can do, what we've been trying to do was, for instance, to see also on EM section the faults. So we can identify faults from the EM sections. And one field of acquisition where, being in Italy, I will really look forward to try to go in terms of research and application is actually in monitoring. So I think that doing monitoring with the EM system, maybe drone-based EM system, for instance, on landslide, this can be really, really interesting. So if we succeed in developing and applying an early warning system made with EM drones that, for instance, monitor continuously a landslide close to an highway or close to a railway, then when it rains significantly, we can fly, we can do a time-lapse inversion, and maybe we can be able to track the risk for a landslide. So this is where I think we might, in the next years, tens of years, I hope only a few years, we might make a difference.
The opportunities for future research.
In general, time-lapse EM inversion, I think is really challenging, but can be really, really interesting.
Perfect. I think let's just give it another minute for more questions from the audience. Yeah. Anyone, any questions? Please type them into the chat, and I'll go through them with Gianluca. We have one question from Alan Jones. These effects have also been reported for natural source EM magnetic rigs, but what about SP?
So set potential. So
is it regional currents causing IP, or is it SP effects of both?
So actually, what has been done is that the set potential has been used for tracking the groundwater flow, because the groundwater flow in itself creates a set potential that then, measuring the set potential, you might get the direction of the water flow in the gradient of the hydraulic head. So this is something that's been done so far. What has not been done so far, but there are probably research projects that start to work on it, is to try to take into account also the variation in the IP effect due to the flow movement of the groundwater. So the fact that the groundwater is moving in itself can give a small variation to the IP effect that we're not taking into account so far for the estimation of hydraulic conductivity.
Perfect. A question from Susan Webb. I was wondering about quick clay mitigation applications.
In terms of mitigation application, I don't know, but in terms of finding the quick clay, maybe. I mean, the clays are for sure good targets for EM imaging, right? So in any case, for sure, airborne EM can be used for doing a characterization and mapping of the 3D heterogeneity in the subsoil. Then in terms of application for mitigation of quick clays, I don't know.
We have a question from Brad Pitts. the possibility of estimating hydraulic conductivity with EM and airborne EM data is an interesting prospect. We look forward to the continued advances in this field.
Me too.
That's
actually
more of a comment.
Here I would like to follow up on this comment as well. So here there are many difficulties. So first of all, I need to be able to fit an entire data set on a big area of, for instance, the area in Brescia of 3,000 square meter, 300 square kilometer, with a fit that is equivalent to the residual inversion. And so far, the difficulty has been mostly in the unsaturated area. But then let's say that we're able to make a model, a 3D model of hydraulic conductivity. Then the challenge and the question mark is, okay, how do we verify or falsify this model? Because of course, comparing the few bores that we have, okay, we can do that, but it's not enough for sure. So question is maybe try to make a groundwater flow modeling based only or strongly based on this estimation from geophysics of hydraulic conductivity, and see if this model itself gives a reasonable prediction. So we're working on this, and again, in this kind of application, it's important to do both, to do your best in terms of estimation of hydraulic conductivity from geophysical measurements, but then we need to do the groundwater flow modeling or transport modeling to see if these estimates they do give an improvement in the prediction.
Thank you. That's great. I don't think we have any more questions, so I'm going to close the session for today. Gianluca, huge thanks for taking your time to take us through your research. We really appreciate it. Please keep us posted on your work. It's very interesting, even from mineral exploration perspective. Huge thanks to our attendees who tuned in for today's talk. Please stay safe and take care of yourself.
Thank you very much, Oleg, and thanks you for the invitation. It has been a pleasure to give this talk for you.
Thank you, Gianluca. Have a great evening.
You too.
Bye-bye.